So I'll be discussing the sample test number 3, which is already on the website, and I shall be doing this in 3 parts. The first for multiple choice, and the second part for the first 2 long problems, and the third part for the remaining 2 long problems. Let's start with the multiple choice questions. First one, you observe a wheel is rotating clockwise and it's speeding up. So we have a wheel that's rotating clockwise and it's speeding up, so which means omega and alpha are in the same direction. Now the way I've drawn it, these curly arrows don't mean much. You have to use a right hand rule to figure out the true direction. So if you work your fingers of the right hand in the direction of omega or alpha, the thumb gives you the true direction. So both angular velocity and angular acceleration point away from you is the correct answer, because pointing away from me means into the page. So the next question asks you to find the torque due to an object being acted on by 2 forces at 2 distances away from the axis of rotation. The axis of rotation is this point, which I'll call point P. So we have to find the sum of the torques about point P. And torque is given by R cross F. So let's first find the direction, R cross F. So you go from R to F with your right hand fingers, and the direction of the thumb gives you R cross F. Same thing here, R2 cross F2 is going to be again out of the page. So we have to add them. The magnitude is R1 F1 sine theta, in this case theta is 30 degrees, plus R2 F2 sine theta, and when you substitute the numbers for R1 F1 and sine theta, which is half, you get the answer E, which is 15 Newton meters. Now for the third question, point A is halfway between point B and the axis of rotation. What is true about A and B is their linear velocities and linear acceleration are connected by these conditions. So point A does not have twice the angular velocity of point B. It has half the tangential velocity of point B. All points on the disk have the same angular velocity, omega, because that's a characteristic of a rigid body. All points have the same angular velocity. So A1 is not true. The angular velocity vector is in the positive x direction. Well, that's not true either, because the angular velocity vector is given by the right hand rule and it's in the positive z direction. Point A and point B have the same angular acceleration. Now, that word is very important. Had they said just acceleration, that would not be true, because B has twice the linear acceleration as A. But they have the same angular acceleration because all points will rotate or start to rotate faster at the same rate. So the only correct answer is 3. Let's go to the fourth question. Now this question is an interesting one because there's a right way and a wrong way to do this. The wrong way to do this is to go to your formula sheet and look at the formula for the moment of inertia of a rod about one end and use that in your parallel axis theorem. That is not the parallel axis theorem, so please don't be tempted to do that. The right way to do this is to locate the center of mass of this first. It's exactly in the middle because it's a uniform rod, and then find this distance d. This distance d is given by subtraction. It's L over 2 minus L over 6. Let's do some common denominator work. That can be written as 3L over 6 minus L over 6, which is 2L over 6, or L over 3. So I have here the moment of inertia about this axis, which I'll call P, is going to be the moment of inertia about the center of mass plus md squared. That is what the parallel axis theorem says. The moment of inertia about the center of mass is 1/12 ml squared, and this is md squared, where d is equal to L over 3. So that's going to be L cubed over 9. And now we have to add 1/12 and 1/9. 36 is the common denominator, so I'll write this as 336 plus 436 and so that's going to be 736 ml squared. Now let me also point out that the wrong answer is also there. The wrong answer that you would have got had you been a little hasty about things. So this part is wrong. I'll write the wrong answer with red. So the wrong answer would have been to say I sub p equals 1/3 ml squared, because you could be confused into thinking you can use either a moment of inertia. Well, 1/3 you may think is more direct because L over 6 is given to you in the figure. So a common mistake that students would usually make in this problem is to write this as 1/3 ml squared plus m times L over 6 squared. And if you did that, you're going to get 1/3 plus 1 over 36 ml squared. This can be written as 12 over 36. 12 over 36 plus 1 is 13 over 36 ml squared, and that answer is right there to trap you. Let's go to the next question. A rock is thrown into the air. At the very top of its trajectory, the velocity of the rock is level with the ground and has magnitude v. The person is observing the rock. What's the angular momentum? Magnitude. So here you have to use the actual definition of angular momentum magnitude, and that is L equals rp sine theta, where p is a linear momentum. That is the definition. The vector definition, it's r cross p for a point particle. And if you expand it out, magnitude gives you rp sine theta. That's what the cross product means. So here, the angle between r vector, that's the r vector, and the velocity vector, well, actually it is this. So if you think about it, that is theta. This is actually 180 minus theta. However, fortunately for us, sine of 180 minus theta is equal to sine theta. You can try it out on your calculator. For example, sine 60 and sine 120 are the same thing. So you're going to end up just getting rp sine theta. Now the momentum is mass times velocity. The d is just r is just d, so it's dmv sine theta. The correct answer is B. Now the next question, a wheel is spinning with 18 radians per second, and it's slowing down with a time varying angular acceleration. So the angular acceleration is given to you. Now because it's slowing down, we're going to put a minus sign in front of it. So alpha, I'm going to dispense with the units for now because it'll slow my work down. So I'll write it as minus 4t. And alpha, by definition, is the rate of change of omega. So from this, you can integrate to find out omega. It's going to be minus 2t squared plus the initial value omega naught, which is the constant of integration. Now it's very important not to use the constant kinematical equations. So I'll write here no to constant kinematics, because this is not a constant acceleration. So that's one of the big cautions. And I'm sure if you use constant kinematics, you'll find one of the decoy answers over there. Now, they want us to find out the time it takes to slow down to half the initial speed, so which means the final speed is omega naught divided by 2. Let's substitute. So I get omega naught divided by 2 is equal to minus 2t squared plus omega naught. Now I have to just solve for it. I can subtract omega naught over 2 from both sides and then take the 2t squared over there. So I get 2t squared equals omega naught over 2. And solving for t squared, I have omega naught over 4. At this point, I can substitute the various values I have. 18 radians per second. Now that 4 actually carries units, so let's put that back there. Radians per second cubed. And so that gives me 9.5 seconds squared. And the final answer is got by taking the square root, the positive square root of 4.5, which is 2.12 seconds. So the correct answer there is B. Question number 7. We have to choose which of these statements is true. A uniform rod swings downward. The angular momentum of the rod is conserved. Well, that's not true because there is an external torque acting, and that's the torque due to gravity. If you notice, the force of gravity is down here, and the torque, which is R cross F, is going to be into the page. If the external torque is not 0, remember the external torque, sum of the external torque is the rate of change of angular momentum by Newton's second law. And if this is not 0, then the rate of change of angular momentum is also not 0, which means angular momentum cannot be constant. Conserved means constant. So that's not true. The rod has a constant torque acting on it as it swings. Now that's not also true because the torque magnitude is Rf sine theta, where theta is the angle between R and F. This angle keeps changing as it swings down. It starts out being 90 degrees and then it ends up being 0. So that's not true either. It swings down at a constant angular velocity. Well, that's not true. If the torque is not 0, the angular velocity, remember torque is the rate of change of angular momentum. Now if the moment of inertia of the rod is constant, I can take the moment of inertia outside, and that's going to be rate of change of, because L equals I omega. I can take the I outside, and it's going to be the rate of change of omega, which is alpha. So if torque is not 0, alpha cannot be 0 either. If alpha is not 0, then this is not true. Also, alpha is not constant because alpha does depend on theta. So none of the above is correct. It's one of those multiple choice questions where none of the answers is correct. The direction of A cross B in this picture, if you'd like, you can bring B right next to A to make it easier to think about. And then you just take your A vector with your outstretched right hand and curl it into the B vector, so it's going to be out of the page. Last question on this page: which of the following is a true statement? The moment of inertia is the same for any axis passing through the center of mass of the object. That's not true. If you take an object and I do it about this axis, it's going to be harder to rotate than about this axis because the mass points are closer. That's not true. The moment of inertia is the smallest for some axis passing through the center of mass of the object. This is actually true, courtesy of the parallel axis theorem again. The parallel axis theorem says that the moment of inertia about any axis P is equal to the moment of inertia about the center of mass plus md squared, where d is the distance between the axis through P and the axis through the center of mass. So that's actually correct. Let's quickly look at the other answers. an object with a non-uniform mass density may have more than one center of mass. That's not true. Center of mass is unique. The center of mass is always contained inside the surface. That's not true either. So you can take a wire and bend it into a weird shape. The center of mass of the wire is going to be somewhere here. It's certainly outside the object. So that's the answer. Let's move on to the remaining questions. Now this question is a classic angular momentum question. The student stands on a freely rotating platform with some initial angular speed, holding weights in both hands. And then the weights are being pulled inwards. Which of the following is a true statement concerning the student and the weights? The moment of inertia decreases. Well, that's true, because the moment of inertia is that of the student plus the weights, and the weights are being brought closer, so that's true. But the angular speed actually increases. You see, because angular momentum is conserved in this process. Li equals Lf, so the angular momentum initial is I initial times the moment of angular momentum initial is I initial times angular velocity initial, and angular momentum final is I final times omega final, and IF is less than II, so that means omega F must be bigger than omega I. So that's not true. The moment of inertia increases and the angular speed also increases. Well, this part is right, but that part's wrong again. So that's not true. The moment of inertia increases and the angular speed decreases. No. The moment of inertia decreases and the angular speed increases. Well, that's not true either. So the correct answer again, I guess, is none of the above. Oh, wait. The moment of inertia decreases, that's true, and the angular speed increases. That's the right answer, because that satisfies both these conditions. Okay. Two blocks are suspended by a cord over a pulley. The masses are indicated. So this is 2m, that's m, so this is going to go down. There's no friction. Which of the following is the correct ranking? So the best way to solve this problem is to simply draw the free body diagrams here. So I'll draw them. This is going to be 2mg, and that's going to be T1. For the pulley, it's going to be an equal and opposite T1 here. And I'll draw T2 as really small because T2 is going to lose out here. Remember, the angular acceleration is going to be in this direction, the linear acceleration is going to be in this direction, and since the string does not stretch, the linear acceleration is the same magnitude but up over there. So if I draw the free body diagram on this one, T2 and mg, so I know that T2 must be bigger than mg, otherwise this won't accelerate up. I know that T1 must be bigger than T2 because the torque must be in this direction. So T1 times R minus T2 times R must be equal to I alpha. So T1 must be bigger than T2. And I also know that 2mg must be bigger than T1 because this is ultimately dragging the whole system. So that's the order, and let's see which one satisfies that. So these inequalities are written in a way that's opposite of what I wrote. So mg is less than T2, that would be this one. So that's correct. It's less than T2 is less than T1. Well, that's true because T1 greater than T2 means T2 is less than T1. And T1 is less than 2mg is the same as that. So A is the right answer. Okay. Now we come to the last two questions. The torque needs to be found. The force is given and the distance is given. Now let me do this on this white space here because it's probably requires some space to do this. There are two ways to do this. First, let me teach you the simpler way of doing this. So torque equals R cross F. Now for simple problems like this, a viable strategy is to simply do the problem. I'll leave out the units. It's 2I hat cross I hat minus 3j hat. That's what I have for R cross F from the problem description. One option is to simply work this out. 2 times I hat cross I hat minus 6 times, let's put this in brackets, I hat cross j hat. Now the thing about I hat and j hat and k hat is that they form a right-handed triple. So I hat, j hat, and k hat are going to be like that. Now when you do I hat cross I hat, it's going to be I hat, the magnitude of I hat, which is 1, times the magnitude of I hat, which is 1, times the sine of the angle between the two, which is 0. So this is going to be 0. I hat cross j hat, if you use a right-hand rule, is precisely k hat. So the answer is going to be negative 6k hat. Very easy. The second method, you actually use what's called the determinant method. Now this formula is there in your formula sheet. So the determinant is formed by writing first I hat, j hat, and k hat, and then putting the value of the r vector. The r vector has only got I component, so it's going to be 2, 0, 0. And the f vector has got an I component and a j component, but no k component. So that's 1, minus 3, 0. And you proceed to evaluate this. So it's I hat times, and the way you do that is to cover up whatever I hat controls and find the determinant of the remaining object. And that's going to be 0 minus 0, which is 0, minus j hat. Now remember, when you do the determinants, you get plus here, minus there, and plus here. So this controls those two things. So I get 2 times 0 minus 1 times 0, which is again 0. The last thing I have is plus k hat, because of that plus sign there, and the determinant of whatever k hat controls, and that's going to be this last thing there. And 2 times negative 3 is negative 6, and 1 times 0 is 0, so it's going to be just negative 6, which is the same answer as we got above, negative 6k hat. So that completes the multiple choice portion. Look for the remaining 2 videos where I do the short problems.